Now, perhaps you've heard of error correcting memory or error correction in communications. Well, in this video, I'm going to show you how that works. I'm going to walk through building a circuit that allows us to encode a message as a series of bits and have that message encoded in such a way that if one of those bits gets flipped, and here we can flip a bit off or flip a bit on, but the message is encoded in such a way that even if we do that, even if we flip one bit, we're still able to decode the message back to whatever the original is by correcting the error that we've introduced. And I'll explain how that works, but if you want a more thorough and truly beautiful explanation of the math behind this, my friend Grant over at the channel 3 Blue 1 Brown made a video walking through that you should really check out. Well, to get a sense of how error correction is even possible at all, you can think of the absolute most simple case, which is error correction of a single bit. We could just store a copy of the bit, and that would let us detect errors, because if we store a 00 but read 10, well, then we know there was an error here. And if we store 11 and read 10, we also know there was an error, but either way, we're reading 10, and we don't know from that what the original bit was supposed to be, whether it was a 0 or a 1. So if we want to be able to automatically correct the error and not just detect it, well, we could store a second copy of the bit. And that way, if we read 100, we would know, okay, well, if we take kind of 2 out of 3 here, if we're assuming that errors are rare enough that we probably only ever have one at a time, then, reading something like 100 probably means the original bit was supposed to be a 0. And if we read something like 101, well, then same thing, sort of 2 out of 3, we figure, well, it's probably supposed to be a 1. So that's a really basic error correction, but it's not at all efficient to store 3 copies of every bit. So can we do better? Well, it turns out we can do a lot better, but we have to think about these extra bits not as copies of the original bit, but as parity checks for it. So what is a parity check? Well, I've got some other videos on parity checks, but basically, if you have a bunch of binary data, you can add a bit that will ensure that the data has an even number of ones. So here we've got 1, 2, 3, 4 ones here. So in this case, it already has an even number of ones. So we could add a parity bit of 0. But if it had an odd number of ones, we could add a 1 there to the end so that in total, all of this has an even number of ones. And that lets us detect an error because if any single bit changes, then it won't have an even number of ones anymore, and we'll know that there was an error. So this is obviously very efficient in terms of detecting a single bit error because you can have as many bits as we like and only a single parity bit to protect them all, and that will detect, I guess, any single bit error. But it won't let us correct it. So another way to think about this scheme where we're storing 3 copies of the bit is to actually think of storing 2 parity checks for the bit, because that's actually going to let us extend it to more bits. But in this case, it looks the same, right? Because with a 1-bit message plus a parity bit, you either have no ones in this case, or you have 2 ones in this case. And those are really the only 2 options with 2 bits to have an even number of ones. And then, of course, the second parity bit here is just a second check. So the nice thing about thinking about these as parity bits is it lets us extend this a little bit. So what I'm showing here is we've got our data bit and we have our 2 parity bits. And I'm just showing here what the different groups are that we're using to compute the parity bits. So we're saying that the data bit 1 and parity bit 1 are used in a combination. And we need to have an even parity between those two. So either they're both 0s or they're both 1s. And then same thing between the data bit and parity 2. They're either both 0s or they're both 1s. But we can extend this by adding another parity bit. And that lets us add another data bit. But the neat thing here is we don't actually need to add 2 more parity bits to get another data bit. We only need to add 1 because we can reuse that first parity bit. So now what parity bit 1 is doing is parity bit 1 is saying that we have an even parity between data 2, data 1, and parity 1. So between these 3 bits, we're going to have an even number of 1s, and we'll just set parity 1 to be whatever it needs to be in order for that to be true. And then if any one of these bits gets corrupted, we can perform these 3 different parity checks and actually figure out which bit it is, because depending on which parity checks either pass or fail, that will uniquely identify one of these bits. For example, if the first parity check between these 3 bits fails, but the other 2 pass, well then we know, assuming that only 1 bit was corrupted, we know that it must be parity bit 1, because if it was one of these other 2, data 2 or data 1, then one of these other parity checks would have also failed. Same thing if only the parity 2 check fails. That would tell us that, the parity 2 bit maybe got corrupted, but all the other bits are fine. But if this first data bit gets corrupted, then both the first parity check of these 3 bits and the second parity check of these 2 bits, both of those parity checks will fail. And if both of those parity checks fail, then that tells us, well, it must be this data bit that got flipped. And we can kind of keep doing that, right? So data bit 2, it would be the first and third parity checks that would fail, and the second one would be fine. But there's actually even more combinations in here, and so we can add a third data bit that is protected by the second and third parity bits, and we just kind of get that for free because that's another unique combination. And in fact, there's one more, which is we can have another data bit that's a part of all three parity groups. And still, if any single bit gets flipped, then a unique combination of these three parity bits will be wrong. And based on what combination that is, then we would know exactly which bit got corrupted. And so this technique of being able to have 4 data bits and add just 3 bits of parity to it and encode that, in such a way that we're able to detect any single bit flip, and not only detect that the bit flip happened, but actually know exactly which bit was flipped. And of course, because a bit can only be 2 values, either 1 or 0, we know how to flip it back, so we can actually correct the error. Well, this scheme is called Hamming 7-4. It was developed by Richard Hamming in the 1940s, actually. And it's called 7-4 because it's 7 bits, and we're able to encode with that 4 actual bits of data. But this scheme, you can extend it as much as you want. If we add a 4th parity bit, we can actually add 7 more data bits, and we'd still have unique combinations of parity bits for all of those. And so it becomes even more and more efficient as it scales up. Now, of course, there's a trade-off because it can only detect a single bit error. So if you have a really big block that you're trying to protect with this, the likelihood of having more than 1 bit error if you have more bits is going to be higher. So there's a trade-off there. But nevertheless, it's a pretty cool way of being able to detect errors, and certainly way better than having to store every bit 3 times. Okay, so how do we actually do this in hardware? Well, the nice thing about this scheme is that because it uses parity bits, the hardware is actually pretty straightforward because you can compute a parity bit basically just using XOR gates. And that's because if you look at the truth table for an XOR, you can see that whatever inputs you get, the output gives you something so that the inputs and outputs together always give you an even number of 1s. And that's actually true no matter how many inputs you have. And the other nice thing is if you have multiple inputs like this, you can chain XOR gates together to sort of get more inputs if you only have a 2-input XOR gate. So this here with these 2 XOR gates, we've got these 3 inputs coming in, and that's going to XOR together these 3 signals, data 4, data 2, and data 1, right? Which data 4, data 2, data 1 makes up a parity group with the parity bit 1 over here. And so this generates that parity 1 based on whatever data 4, data 2, and data 1 happen to be coming in over here. And we're basically just doing the same thing with XOR gates to generate parity 2 based on data 1, data 3, and 4. And then parity bit 3 is based on data 2, 3, and 4. And that's really it to create this circuit so that whatever data is coming in here, it'll generate the appropriate parity bits so that we're guaranteed to have even parity across these 4 bits, across these 4 bits, and across these last 4 bits. So let's go ahead and build this circuit and see how it works. Okay, so we're going to need a bunch of XOR gates, and for that we can use the 74LS86, which is just a chip that has 4 XOR gates on it, just configured like that. So I'll use a couple of these chips, since we'll need a bunch of XOR gates. And then for the inputs, I'll just hook up some dip switches so we can set whatever input we want. And I'll have one side of the dip switches tied high through these 1K resistors, and then the other side of each switch I'll just tie directly to ground. That way on this side we'll have 5 volts through the resistor, but then when we turn the switch on, which is actually pushing it down, then it'll connect it through to the ground and bring this top side here to 0 volts. So we'll either be at 5 volts if the switch is up or 0 volts if it's down. And so that's how we can set our 4 bits. Now I just need to wire this up just like this. So I'll take the first couple XOR gates, and well, I guess the first XOR gate will be this one. So I'll tie it to D1 and D2, which will just be switch 1 and switch 2 here. And actually, before I forget, let me hook up the power and ground to each of these chips as well, so they're powered. So those are two inputs of an XOR gate, and then the output of that will go into the input of another XOR gate. There's the output going around to another input, and then the second input of that goes to D4. And so that's these first 2 XOR gates hooked up. We've got D1, D2, and D4 all XORed together to get us that first parity bit. So you can see D1, D2, and D4 are hooked together, and that first parity bit will be on the output of this XOR gate right here. So now I'll go ahead and hook up the other XOR gates to be able to generate the other two parity bits. So parity bit 2 is going to be hooked up to D1, D3, and D4. And parity bit 3 is hooked up to D2, D3, and D4. Okay, and that's it. So we've actually got all of these XOR gates hooked up, and we've got our inputs over here on the switches. So somewhere in here, we've got our four data inputs, as well as our 3 parity bits are kind of in a couple different places here coming off these chips. So now what I'll do is hook up some LEDs so we can actually see what all 7 of these bits look like a little bit easier. So this will be the 4 data bits as well as the 3 parity bits in the same configuration here, so we can easily see what's going on. So first I'll get the 4 data LEDs hooked up. So the green LEDs are data, and those are hooked up through to those dip switches. So this should just show us exactly what we're inputting on the dip switch. And then I'll hook up the 3 parity bits to the outputs of those final 3 XOR gates. Okay, so now we've got this entire circuit hooked up, and we've got the LEDs over here so we can actually see what the outputs are. So now I'll hook up 5 volts, power this up, so we can start to play around with it and kind of get a sense for how it works. So if we start setting these dip switches, you'll see, as I flip these dip switches around, the output changes. And of course, the green LEDs, the 4 green LEDs, just match up directly with the 4 dip switches. So whatever I set these dip switches to, you'll see I've got 1, 1, 0, 1 over here. I've got 1, 1, 0, 1 if we just look at the green LEDs. But then the red LEDs will just sort of change around to match whatever they need to have the correct parity for these different parity groups like we talked about. So just to get a sense of how that works, if we look at the first parity bit over here on the right, this parity bit is covering these 4 bits, if we look at every other bit. So if we look at, D4, D2, D1, and then the parity bit, we see we have 0, 0, 1, and then the parity bit is a 1. And remember, the goal is that the parity bit should be either on or off to ensure that there's an even number of 1s within that group. So we have 0, 0, so we have a 1, we have 1, 1 here, so we need another 1 in order to have 2 1s in that group so that 2 is an even number, and we have the even parity. So that's why that parity bit is on, to ensure that that's true. Now, if we look at parity 2, that covers these 2 bits and these 2 bits. And so if we look here, between these 2 bits, we've got 1 that's on, and then if we add in this bit, we've got a second 1 that's on. So the parity doesn't need to be on in order to ensure an even number of 1s, an even number of bits that are on within that group. So that parity bit's off. And then parity bit 3 covers just these last 4 over here on the left. And so we have 0, 1, 0. And so because we have 1 LED on there, we need to turn on this second one in order to ensure that there's an even number of 1s within that group. And because of the way we've wired up these XOR gates, as we switch these on and off and adjust our inputs, the output's going to change automatically to ensure that this is always true. And what this does for us is that if we have some sort of bit error, so let's say like this bit here is supposed to be a 1, it's on right now, but let's say there's some kind of error in our storage or transmission or whatever we're doing with this data, where that bit, it's a little bit flaky, and maybe it's actually accidentally off. There's some kind of bit error that has happened, and so that bit is off. Well, we can still, with this information alone, recover the original message, which is 1010. And the way we do that is we just check each of the parity bits. So parity bit 1 here on the right covers every other bit. So if we look at every other bit, we've got a 1, 0, 0, 0. Okay, so that right there is suspicious because within that group, we should have an even number of 1s. So we should either have 0 1s or we should have 2 1s or 4 1s, but we shouldn't have 1 1, right? And so there's a problem. So we have 1, 0, 0, 0. So we only have 1 1 within that group. So parity bit 1 seems to be wrong. But let's keep going. So parity bit 2 is on, but let's see if it's supposed to be. So with parity bit 2, we're looking at these 2 bits as well as these 2 bits. That actually looks right because we've got a 1, 0, 0, 1. And so we've actually got 2 1s within that group. So parity bit 2 should be on, and so that seems fine. But now let's look at parity bit 3. So parity bit 3 is these last 4 bits. So we have 1, 0, 0, 0. Well, that's wrong because we only have a single 1 within that group. And a single 1 is not an even number because 1 is odd. So that parity bit 3 is wrong. So we've concluded that parity bit 1 is wrong and parity bit 3 is wrong. And the only case that's covered by parity bit 1 and 3 being wrong plus parity bit 2 being right is this case here. So if both of those are wrong, but parity 2 is right, then we can conclude that D2, this bit right here, is wrong. That's the culprit. So if we look at that bit, we know that that's wrong. Well, if we look at it, we can see that it's a 0. So if we know that it's wrong and we see that it's a 0, then we can correct it by just flipping it to a 1. And so if we assume that, okay, this really should be a 1, then our true data is 1, 0, 1, 0. And that, in fact, of course, is right, 1, 0, 1, 0. So that's how this Hamming code error correction works. But of course, the next question is, okay, we went through this whole process by hand to figure out that there was an error and then which bit it was. And then, of course, to flip it. But how can we do that in hardware as well? But actually, before we get into decoding this, first we actually need a way to easily insert some errors here without just sort of like unplugging things. So I have this other circuit here that I built ahead of time, and it's actually, pretty straightforward. So let me just explain what it does. I've got 7 inputs coming in over here, and those inputs go into XOR gates, each one going into one side of an XOR gate. And then the other side of that same XOR gate, I've got 7 switches here that I can toggle. And the way that an XOR gate works, if you look at it, is if one input is off, so let's just look at the top half here where the A input, both of those are 0, well, you can see the output just follows whatever the B input is. But if we toggle that first input on, then you can see the output is the opposite of whatever B is. And so that's basically what I'm doing here, is I've got an XOR gate where the A input you can think of is these dip switches. And so if they're all off, then the outputs of the XOR gate is going to be whatever the input is. So I've got 7 inputs here, I've got 7 outputs. The outputs are going to be the same as the input. But if I toggle one of these, then it will flip that particular bit. And if the bit was supposed to be a 0, it'll flip it to a 1. If it was supposed to be a 1, it'll flip it to a 0. So this lets me pretty easily just flip bits. So I'll hook up the 7 inputs of this to the outputs of the Hamming encoder that we just made. So there we go. And then I'll also just connect the power here, power and ground through, except I'll hook it up the right way around. And there we go. So what we should see is we should see this be the exact same. So whatever we've got here in the top, we should see here, except that I can flip a bit. So if I want to flip, let's say this first data bit here, or bit 3, just flip it and that'll turn it on. If I want to flip the second bit, I can flip it off just by flipping the switch here. So this circuit just lets me introduce whatever error I want so we can test out the error correction that we're about to build. And the way the error correction is going to work is we want to be able to basically compute each of these parity bits and see which of them are wrong, because it was by checking each of the 3 parity bits that we were able to determine, based on the combination of which parity bits are wrong, if any of them are. It was from that combination that we're able to determine which bit was off. But we need to first compute those parity bits and figure out if any of them are incorrect. And so the way to do that is more XOR gates, because XOR gates are great at computing parity. So what we'll do is we'll have 3 sets of them to compute the 3 different parity bits. So this first set here is for parity bit 1, and it's going to have 4 inputs here. And basically what this is going to do is XOR them all together. And so if there's an even number of 1 bits coming in here on the left, then the output will be a 0. But if for some reason there's an odd number of 1s coming in here, so basically either 1 of these or 3 of these are 1s, well then the output here is going to be a 1. And so a 1 on any of these things indicates that that parity bit was wrong, or there's some kind of problem that involves that group. And so we just do that for the 3 different groups. And so you can see this one is hooked to the same, every other bit like this. So you can see it's just hooked to every other bit. This second set of XOR gates is this set here on parity 2, and it's these 2 and these 2. And so you can see it's, those 2 and then those 2. And then finally, parity bit 3 is coming around and hooked to these XOR gates here. And you can see it's just these 4 here. And so it's those 4 being XORed together. So this will compute those 3 parity bits. And if there hasn't been a bit flipped, then these should all be zeros. But if any of these are a 1, then that means that something has been flipped. And then depending on which combination of them are 1s, well, we can figure out which actual bit exactly was flipped. So let's go ahead and build this, and then we can play with it, and I'll show you exactly how it works. All right, so here we've got some more XOR gates. And I'll get the power and ground pins hooked up on each of these chips. And I'll start by hooking up this last group here, because that'll be the sort of the last 4 bits which have been on the left, kind of the way we've been laying things out. So I'll put that on the left here. So those bits will just come into, 2 of them will come into the input of one XOR gate, and then the next 2 will come into the input of another. And then the output of the first XOR gate will come around to one of the inputs of another XOR gate up here on the top. And then the output of the other XOR gate down at the bottom will go around to the second input of the XOR gate at the top. And then the output of that XOR gate we can just hook up to an LED, and that'll let us see what's going on there. So that's this bottom one here. So we've got those 4 inputs coming in, going through 2 XOR gates, and then the outputs of those going through a third XOR gate, and then we've got this LED looking at the output. So next I'll hook up these XOR gates. And so 2 of the inputs are these 2, and then the other 2 inputs are the next 2 here. Hook those up there like that. And then again, the outputs of these 2 XOR gates on the bottom are going to go around to the inputs of an XOR gate on top. And then the output of that XOR gate on top, we'll stick an LED here so we can see what's going on with that. And so now that's this the second one, or that's, yeah, the second one here. So it's going to those 2 inputs, same 2 inputs there, and then these 2 inputs here. So lastly, we'll do this one, which is just going to look at every other input. All right, so that's every other bit being input into those 2. And again, we'll take the outputs of these 2 XOR gates around to the 2 inputs of an XOR gate on the top, and hook an LED up to that one. So there we go. So now we will get an output on these 3 LEDs to show us which of the 3 parity bits is, if any, I guess, is incorrect based on the input that we've got. So let's hook all this up to what we've got already. So I'll hook this up to the output of that error injector circuit thing that I just showed you. So now I've got all that hooked up. Let's hook up power to this final circuit down here. And there we go. And let's see, we have a problem with this bit here. Yep. It's funny, I knew exactly which wire was was wrong, which I'll explain in just a minute here. But what this is showing now is it's showing the parity bits. So right now we don't have any errors injected, so all of the parity bits check out. But let's say we were to inject an error. Let's say we're gonna inject an error into bit 3. So right now, bit D3, the second bit here, is off. Let's say that some sort of error occurs that flips that on. Well, that's going to screw up these 2 parity checks here, the parity check for bit 2 and parity check for bit 3. So let's do that. So if we flip that, we flip that on. Now we see that those 2 parity bits are wrong. And so we know that if we know that those 2 parity bits are wrong, that's, this one and this one. If we know that those 2 are wrong, the only case where both of those could be wrong is if bit D3 is flipped. So if we look at what we've got here, we can see bit D3 is a 1. So if that's been flipped, then we know it should be a 0. So if we flip that around and look at that as a 0, well, then we end up with the correct answer, which is what we've got up at the top. So just by checking those parity bits, we're able to figure that out. So if I flip another bit here, so in this case, only one of the parity bits is wrong, and that's parity bit 3. So that's this case here. So in this case, the error is actually parity bit 3. The data is fine. The only bit that's been flipped is parity bit 3. Let's say I flip a different bit. Well, in this case, I see parity bit 1 and 2 are wrong. So in the case where parity bit 1 and 2 are wrong, that's this case here. So 1 and 2 are wrong. That must be that D1 has been flipped. So D1 shouldn't be a 1, it should be a 0. So at this point, we're actually able to detect any single bit error. So in this case, this is going to be a D3 again, D2. We can detect any single bit error just by looking at which parity bits are wrong. And of course, if they're all off, well, then that means that there's no error, and what we're receiving here is correct. That matches what is being sent, or what we're reading is matches what was stored if we're doing error correcting memory or something like that. Now, obviously, the one caveat is if there are 2-bit errors, then all bets are off. So in this case, what we're seeing is we're seeing parity bit 1 and 3 are wrong. So the case where parity bit 1 and 3 means that D2 must be wrong. So if we try to do error correction here, well, if we flip D2, we'd get 1, 1, and then that would be a 0, 1. Well, the data was, 1, 0, 1, 0. So we're not going to get the right answer in that case, but that's because we've got 2 errors. I've injected an error on D1 and D3. So we're not able to correct 2 errors, but if there's any single bit error, no problem. We're able to detect it, and we're able to figure out from what parity bits are set, we're able to figure out which bit was flipped. And so presumably we can build a further circuitry here to actually flip it back around the right way. But before I get to that, one thing that you might have noticed is that the way that this is laid out, perhaps you've wondered why I sort of interleaved, parity 3 in the middle here, why it's kind of grouped like this. Well, it's grouped like this because the way this is laid out, the actual parity bits here read out exactly which bit is wrong. So if we look at this in binary, we see 0, 1, 1. Well, that's 3. Well, 3 is 1, 2, 3, the third bit, D1. So 3 is in fact the bit that was flipped. And it's, the same for any bit here. So here I see 1, 1, 0. Well, 1, 1, 0 in binary is a 6. So that must mean that bit 6 was flipped. And in fact, it was. So whatever bit I flip bit 5, I get 1, 0, 1. That's a 5 in binary. And that's actually why, funny enough, when I first hooked this up, you remember I had this wire just off by 1 like that. And I immediately knew, just by looking at this, I was like, wait a minute, something's wrong with bit 1. So did I hook bit 1 wrong? And I did. I had it off by a little bit. So that's, I guess, the nice thing about working with error correction circuits is that if you have an error in your circuit, it tells you about it. And not only that, it tells you how to correct it. So it told me that bit 1 was hooked up wrong. So there we go. But anyway, now that we are able to figure out, okay, bit 3 is wrong, the next thing you want to do is, if we're using this in some circuit, presumably if we stored this particular data, 1, 0, 1, 0, we want to be able to read 1, 0, 1, 0 from somewhere. So we've got this error, this data with an error in it, and we know where the error is. So the next thing we want to do is build a circuit that actually takes the information about where the error is and uses it to actually correct the error. So how do we do that? How do we use that 3-bit binary position of which bit has the error to actually flip that bit back to the correct value? Well, we can use a circuit like this. So what this is we've got our 4 data bits coming in, and if we just look at one of them, we've got that data bit coming in, and it's going through an XOR gate. And remember, with an XOR gate, if the other input is a 0, then the output's just going to be whatever the input is. But if that input is a 1, then the output's going to be the opposite of whatever the second input is. So that's what we're doing here, is we're taking the bit, and if this other input, this bottom input, is a 0, well, then the bit just passes through. If the bottom input is a 1, then it flips the bit. And so then what we just need to do is we just need to figure out, does that bit need to flip? Is that the bit with the error? And the way to do that is with a simple decoder circuit, and that's what these AND gates are. So these are AND gates that say, okay, if all 3 inputs are 1s, then the output is going to be a 1, otherwise the output's a 0. So if all 3 of these inputs are a 1, then it flips this bit, otherwise it doesn't flip the bit. And then we can position an inverter on whichever inputs we want to be able to use this AND gate to select a particular value from these 3 bits. So in this case, we're selecting the value 1, 1, 0. Or actually, I think it's the other way around. I think it's 0, 1, 1. Yeah, so 0, 1, 1, which is a binary 3. And so that's actually going to select that first bit position, right? So if we have a 3 coming in here, so 0, 1, 1, that means that we have an error in the third bit position, which is D1, and we want to flip D1. This AND gate here, we have 1, 0, 1, and 1, 0, 1 is 5 in binary. So 5 is going to be the fifth bit position. So 1, 2, 3, 4, 5, that's D2. So we have that 1, 0, 1, we're going to flip D2. We're going to flip that 5th bit position. Here we have a 1, 1, 0. So in the case that we've identified our error is in in bit 6, 110, then we'll flip D3. We'll flip the 6th bit position, 1, 2, 3, 4, 5, 6. And then, of course, if we are 111, that's the 7th bit position, and we'll flip this last bit. So this decoder circuit will let us use the binary information we have. So in this case, we see that the error is at 011. So 011 is bit position 3. So that means that the error here is in bit position 3, which will activate this AND gate. Of course, none of these others will be activated because they're selecting for different combinations of values. But this one will be on. And so that will tell this XOR gate to flip its input. And the other ones won't flip their inputs, so they'll just pass through. But this one will flip, which will have the effect of correcting the bit that was incorrect. So let's go ahead and build this part of the circuit. Okay, so to build this out, we need some XOR gates, some AND gates, and some inverters. For the inverters, I'm going to use the 74LS04, which has got 6 inverters on it. We only need 3. And for the AND gates, I'm going to use the 74LS11, which is this 3-input AND gate. And there's 3 of them per chip. We need a total of 4, inconveniently. So I guess we'll need 2 of these chips. And then finally, more XOR gates, so the 74LS86 again. So go ahead and power all these up. And then finally, the output here, I just want to hook up some LEDs. And it's getting pretty tight over here on the edge of this breadboard, but I think I can squeeze in 4 LEDs just to be able to see the 4 data bits that we started with. And then connect each one up to the 4 different outputs of the 74LS86. So there's 4 XOR gates in this last chip here. And I'll just connect one of these LEDs up to the outputs of each of those 4 XOR gates. And I'm connecting them through just a 220 ohm resistor. So there's some extra current limiting through the LEDs. And I think what I'll do is just kind of work backwards, connect these inputs from the 4 XOR gates to the outputs of the 4 AND gates. So there we go. We've got the 4 outputs of the AND gates hooked to the 4 inputs, or 4 of the inputs of the 4 XOR gates. So then I've got a bunch of these connections here on the inputs of the AND gates to hook up. And a lot of them are kind of hooked to each other, kind of 2 inputs connected to each other. So I'm going to try to hook these up as efficiently as I can here. Okay, so that's all of these connections, I think. We're seeing all of these LEDs on except for the last one, which I think makes sense because we don't have any of these 4 connections hooked up yet. So I think these inputs are going to all default to 1s, except for this one. Well, it's going to default to a 1, but it's going to be flipped because that's the bit where we've introduced the error. If we don't introduce that error, then it's all going to default to 1s. So I think everything's working so far. We just need to hook up that second input for each of those XOR gates, which are these original data bits, and then it'll flip the one that's wrong. So here is data bit 4. That stays on. That makes sense. Data bit 3. Data bit 3 goes off. That sort of makes sense. Data bit 2 is here. That one's on. That makes sense. That matches what it should be. And then finally, data bit 1. And if we hook that up, that's off, which is not what it is here, but it is what it is here. So it is correcting that. And so if we start introducing other errors, what we see is that regardless of which bit error we introduce, the output remains the same. And of course, if we change the input, that'll change the output. And the output will always match the input. But if we have any single bit error, what we see is that our output doesn't change. We're correcting that error. Of course, if we have 2 bits of error, well, then the output changes, but that's just not something that the circuit guarantees. This is only able to correct a single bit error. And of course, that is the inevitable trade-off that always exists. That's the trade-off with this particular scheme, is that we can add more and more bits, and the more bits we add, the fewer sort of relative parity bits we need. So we could expand this by adding 1 more parity bit, and we'd get to add 7 more data bits, but it would still only be able to correct a single bit error. So if you expand this too much, then the probability of having 2-bit errors goes up more than it would if we just kept it smaller like this. But that's the trade-off between efficiency of covering more data with fewer parity bits overall versus the accuracy of being more likely, I guess, to be able to correct an error. Though one thing you might have noticed with this particular scheme is that the way it works is like the most efficient scenarios here are always like 1 less than a power of 2. So what we've got here is we've got 7 bits. And 7 is kind of a weird number in computer science and computer engineering. You usually expect a power of 2. You expect 8 bits. So why don't we have that extra bit? Well, the reason is that it wouldn't really work, because if we did have an extra bit here, the indication that there's an error with that bit would be if all of the parity bits pass. So like we wouldn't be able to distinguish between this situation here where we have 0, 0, 0 indicating an error in position 0 versus 0, 0, 0 indicating that there's no error, which is of course what it indicates now. So a common thing to do is, usually when you're storing stuff, you have 8 bits to work with, you wouldn't have 7 bits, or if we expand this out, you'd have 16 bits to work with, you wouldn't have 15. Common thing to do is to use this extra bit as a parity bit for all of the bits. And it doesn't help you with error correction at all, but what it does do is it gives you a second check so that if you have an error that you're able to correct, and you have another bit that's wrong, then that extra parity bit will tell you if you have a 2-bit error. So that's a very common use of that extra bit. Now, I won't build all the circuitry to add that, but you can use your imagination there. But that means that in practice, this Hamming code scheme will usually let you correct 1-bit errors and detect any 2-bit errors. And if you want to learn more about how that works, or if any of this was in any way interesting, I strongly recommend checking out Grant's videos over at 3blue1brown. He's got a beautiful video that explains Hamming codes from a different perspective, and another video coming soon that discusses a really elegant software implementation. So definitely go check out 3blue1brown. And of course, as always, thanks to all my patrons. Your continued support helps make these videos possible, so thank you.